In this slide deck, we are going to learn how to read graphs of two variables. And then we'll use this graph of two variables to understand a very, very fundamental core concept in economics, which is called the model of demand and supply. And the model of demand and supply is just going to be graphs of two variables. As we spoke earlier, that a model is just a representation or just a tool that is used to tell economic theories or stories. This demand-supply model is just going to be a tool to tell stories in terms of how markets work. For example, where does price come from in a market? So those kind of questions will be answered by this demand-supply model. We'll read that later on, but right now let's just first learn how to read graphs of two variables. So in any graph of two variables, what we're trying to see is how a variable x and y, let's say x is quantity of, let's say, a video game buyers buy, and y could be price of that particular video game. And in this graph of two variables, we always have two axes. One is this horizontal axis. Traditionally, it's called the x-axis. And the other one is called the vertical axis. And notice that each of these two axes are basically number lines. If you look at this horizontal axis, it's a number line where I'm starting from 0. And as I go rightward, the value increases. The value of whatever I'm measuring increases. As I go to the left, value decreases, and below 0, it becomes negative. Similarly, the vertical axis is a number line 2. As I go upward, value increases, so on and so forth. So just a quick recap. To make a graph, we really need these two number lines, which we call two axes, and horizontal and vertical axis traditionally are called x and y axis. But you could also call these two axes in our context that this is the quantity axis because I'm measuring how much quantity of a particular product, let's say a video game, is going to be bought or consumers will want to buy at what price. Now the y-axis is going to become price axis. So when these two axes intersect each other at the point, that point is called point of origin. Usually we take this point as a 0 value. When you are right here, your quantity axis, quantity value is 0, price value is 0. If you go to the right, let's say here, your quantity value is 10, 20, so on and so forth. If you go upward at any point in this quadrant or in this space where my circle is hovering, if you go upward, that will mean price is increasing, or the vertical value, variable's value is getting bigger and bigger. So position of any point in this space can be expressed just by two numbers. Those two numbers are, 1, how far away is A from 0 horizontally? So for example, in our case, this point A is horizontally 10 units away to the right of this point of origin. And vertically, this point is 1 unit above 0. So these two numbers are traditionally written as the coordinates of this particular point. So point A has a coordinate of x equal to 10 and y equal to 1. In other words, point A is indicating in this graph of price and quantity of the video games that people buy as when price is $1 per unit, or 1 unit could be $100, we don't care, whatever the unit is. When price is 1 unit, total amount people will want to buy is going to be 10 units. That's this 10 and 1, these two coordinate points are measuring. And similarly, we can find coordinate of any other points. For example, let's say if I'm right here at point B, then point B's coordinate would be I am 30 units to the right from 0 and 0 units to the vertically away from 0. So that simply means that if price was $0, lot of quantity would be bought, people would just go crazy and buy 30 units, right? So this 30 is whatever unit you're measuring. This 30 could be 30,000, 30 million. We don't care. We're just building theory by using these arbitrarily chosen numbers. So now, let us see an example of a use of a graph. Here I have another graph. I will plot another graph where horizontal axis will measure time, right? As you go from this zero to the right, time will increase. Calendar years are listed here. So 1988, for example, is bigger than 84 because it is to the right. And on the vertical axis, suppose somebody is measuring price of coffee in a particular country in terms of dollars, right? And let's say they found different prices for different years, and they let's say in 1980 they found a price of coffee was equal to about $1.5 per pound. In 1992 they found price was equal to, let's say, $0.6 per pound, so on and so forth. And this red line that you are seeing, it is nothing but connection, all right? They just connected all these many different prices found from many different years, and they found this kind of a joining line, which they call graph, showing the price movements of coffee over time. So graphs are really convenient, and when you go to your university programs or if you start working for a company, manufacturing company, sales company, marketing company, etc., in many occasions people will give presentations by using graphs, because graphs convey a lot of information in one single piece of paper, right, or image. For example, this graph is telling me what was the lowest price over this period of time, what was the highest price over this period of time, right? And then it's also telling me between which 2 years price was mostly falling, between which 2 years price was falling faster. For example, you can see that between this year and this year here, within a very short period of time, price just fell from more than $2 to only close to 50 cents, right? In between which 2 years price was rising very fast, so on and so forth. So all those things can be, all this information can be conveyed in a single piece of picture. That's why graphs are really frequently used in all sorts of presentations, research papers, and talk points. All right, so now let's see what kind of relationships we can sometimes either tell by using common sense or by using empirical data. Two types of relationships can be conveyed. Usually these two types are conveyed. Sorry, this is just one type listed here, my mistake. One is positive relationship when both variables are changing in the same direction. A positive relationship between two variables exists whenever one variable's increase is associated with the other variable's increase, and vice versa. If one of them decreases, the other also decreases. If we see that kind of a trend, we say that these two variables are positively related. And by the way, in economics, most often what we try to understand is relationships between variables. For example, what would happen to price level if central banks decrease interest rates? What will happen to home prices if mortgage rates are higher? What would happen to consumer demand if we reduce the price of our product by 50 more cents, so on and so forth? So lots of questions are regarding relationship between two variables. That's why we are trying to explore possible portrayal, possible display of relationships shown through graphs. So here's an example of a positive relationship between two variables. Here we are measuring a relationship between how fast a car is being driven, let's say on a straight line, right? Speed, miles per hour. And on the vertical axis, we are measuring in 5 hours how much distance the car will cross. So this is a common sense idea that, well, if I drive faster, then every 5 hours I'll cross more distance. And this is going to be a straightforward relationship. For example, if somebody is driving a car at 20 miles per hour, in 5 hours, they will cross 5 times 20, 100, 5 times 20, 100 miles. So in this graph of two variable, that that relationship between 20 miles per hour and 100 miles could be shown by, for example, this point, point A, that is telling me that when speed is 20 miles per hour, distance crossed will be 100 in 5 hours. Similarly, if I'm driving my car at, say, 60 miles per hour, in 5 hours, I'll cross 60 times 5 equal to 200 miles. And, oh, sorry, 60 times 5 is 300. That's my mistake. And then we'd find another coordinate point that coordinates or shows relation between this speed 60 and this total distance crossed 300. So now, if I just connected point A and B with a line or with a curve, what I find is an upward sloping line. What do we mean by upward sloping line? Upward sloping line means if you take any 2 points on a line in a graph, and then if you just slide from the left point to the right point, if you're also rising upward, then these two variables are positively related, and this graph is going to show you positive relationship. Notice that we read graphs just like we read English language. We read English language from left to right. Whenever we read a sentence, we start from the left and we keep on going right. Similarly, when you read a graph, take any 2 points and start from the left point and then move to the right. So now, if in a graph, when you are moving from left to right, let's say when speed is increasing, if you're also moving low to higher on the vertical axis, if you're moving upward, then these two variables are positively related. That simply means that when speed is increasing from 20 to 60 in our case, distance crossed is also increasing and vice versa. So now we know what positive relationship means. And by the way, let me take you to the previous slide. Positive relationships are sometimes also called direct relationship. And the example that we saw in the next slide is showing us a linear relationship, which means the relationship shown between speed and distance crossed in 5 hours was a straight line relationship. In our real world, most of the relationships are not really linear because real world is much more complex when it comes to economic variables, such as what will happen to quantity purchased if price decreases, so on and so forth. Those relationships are most often not really linear, but to keep our story simple, we will, throughout our course, assume that these relationships are linear and will most of the times draw straight lines, right? That is just an assumption. So now let us see an example of when two variables are not positively related, but negatively related. So let's see this really peculiar, silly example. I just made this silly example to make you laugh a little bit, I guess. So let's say we are plotting two strange variables on a graph of two variables. On the vertical axis, I have height of a person, how tall a person is. And now I'm asking you to imagine that on the horizontal axis, you will create an imaginary scale, say on a scale of 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say from a scale of 0 to 10, 0 meaning not funny at all, and 10 meaning, wow, that's extremely funny. How funny would it be when the person is completely drunk and he's trying to dance? So this particular graph is asking you to imagine that maybe height of the person, how tall the person affects how much funny it will look when he's completely drunk and starts to dance. So if I ask you that, imagine a very tall person. Let's say the person is 7 feet tall. He's a basketball player or something. And he's completely drunk and he's trying to dance around you guys. How funny would it be? Many of you might say, yeah, it'll be funny, but maybe many of you would say that, actually, personally to me, it might be more scary than funny because a 7 feet tall well-built person, if he's completely drunk and dancing, what if he falls on me or something, or accidentally hits me? It's kind of maybe it's a little bit funny, but not that much funny. I'm mostly scared in this case. So level of funniness when the height is very tall might not be very might not be a lot. When the height is 7, somebody might say, yeah, on a scale of 0 to 8, maybe I would think that it is funny at the level of 3, right? So point A would be a coordinate point that would coordinate very tall height to only 3 level of funniness on a scale of 0 to 10. And then if I asked you that, well, now imagine that a midget or a let's say 10-year-old kid is completely drunk, and they're trying to dance, or let's say just a 3 feet tall or 4 feet tall um, dog is completely drunk and they're trying to dance. How funny would that be? Then most people might say that, wow, that's a funny image. Now I'm not scared anymore. So if I take lower height, then maybe somebody would rank that, yeah, that's quite funny. I would rank it at level 7 funny, right? So similarly, if we plotted some other random points that how funny it is when somebody is 5 feet tall or 6 feet tall, so on and so forth, then we would find a locus of points. And then if we connected these dots or points with a line, what we would find is a downward sloping line. Again, downward sloping line means after taking any 2 random points, if you slide along the line from left to right, again, just like English language, we read graphs from left to right. If you slide from left to right, if you're at the same time also moving downwards, then there's a negative relationship. When one variable is decreasing, the other variable is increasing. So this is an example of a negative or inverse relationship. So now we know how to depict a graph and read graphs of 2 variables. And the next topic that we'll now learn by using these concepts is to see how buyers behave in a market, and can we depict theoretically behavior of buyers by using a conceptual or theoretical graph. All right, so we'll do that in the next